For nearly a century, one stretch of ocean has carried a reputation no other place on Earth shares. Ships entering it have vanished without wreckage. Aircraft have disappeared without a single distress call. Compasses have spun without explanation. We call it the Bermuda Triangle. For decades, the explanations on offer were strange. Lost cities, time warps, forces beyond science. But in the last several years, something has shifted. Scientists studying this region are no longer reaching for the supernatural. They are reaching for satellites, sensors, and seafloor maps. And what they are finding is, in some ways, far stranger than fiction, because it is real. This is what they have actually discovered. First, the scale of the mystery, stripped of exaggeration. The Bermuda Triangle is a roughly triangular region of the western Atlantic Ocean, bounded loosely by Miami, Bermuda, and Puerto Rico. Across decades of recorded history, it has been linked to the disappearance of an estimated 75 aircraft and hundreds of ships. That number sounds enormous, but context matters. The triangle sits along one of the busiest maritime and air corridors on the planet, heavily trafficked by recreational boaters, private pilots, and commercial vessels for over 100 years. The U.S. Coast Guard, which has investigated incidents in the region for decades, has stated repeatedly that the number of disappearances is not statistically unusual compared to other heavily trafficked ocean regions of similar size. That single fact reframes the entire mystery. The triangle may not be uniquely dangerous. It may simply be uniquely watched. But not statistically unusual does not mean fully explained. Real incidents happened. Real ships and aircraft were lost under genuinely strange circumstances. And several independent lines of scientific research have converged on natural explanations that, individually, are each compelling. The first major theory involves the ocean floor itself. Beneath large areas of the seafloor, bacteria slowly break down organic material in the absence of oxygen, producing methane gas. Under the right conditions of cold temperature and high pressure, that methane becomes trapped in ice-like structures called methane hydrates. Essentially, frozen cages of gas locked within the sediment. Researchers, including teams at the Arctic University of Norway, studying similar formations elsewhere, have found seafloor craters consistent with sudden, large-scale methane hydrate eruptions. If a sufficiently large pocket of trapped gas ruptures, triggered by seismic activity, a shifting fault line, or pressure changes in the sediment, it can release an enormous bubble of methane in a very short period of time. The physics of what happens next is the unsettling part. As that gas rises through the water column, it does something seawater is never supposed to do. It makes the water dramatically less dense. A ship floating on water of normal density can lose buoyancy almost instantly if it passes directly over a large enough gas release. Oceanographers studying this phenomenon have noted that a ship caught above a large methane eruption could, in theory, sink within seconds, far too quickly for a crew to send a distress signal, and quickly enough that no wreckage would remain on the surface to investigate. For aircraft, the danger is different but related. If methane gas reaches the surface and disperses into the air above, it can lower the density of the air itself. Aircraft engines depend on a precise mixture of oxygen to function. A sudden pocket of methane-contaminated air could, in principle, cause an engine to stall. Importantly, scientists studying this theory are careful to note its limits. No controlled experiment has ever proven this can happen at the scale required to sink a large vessel. And methane hydrate deposits are not unique to the Bermuda Triangle. They exist in seafloor regions across the globe. Norwegian fjords, the Gulf of Mexico, the Sea of Japan, and many other deep water zones contain similar deposits without an equivalent reputation for disappearances. So methane gives us a real physically grounded mechanism. It does not give us a Bermuda Triangle specific answer. The second major discovery comes not from the ocean floor, but from the sky above it. In 2016, meteorologists studying satellite imagery from NASA's Terra satellite identified something unusual hovering above the Bahamas, near the edge of the Triangle region. Clusters of hexagonal-shaped clouds with unnervingly straight edges. Clouds, by nature, are chaotic. They do not normally form geometric patterns. Dr. Steve Miller, a meteorologist at Colorado State University who studied the imagery, noted that straight edges are simply not something you typically observe in cloud formations. Clouds are, by their nature, randomly distributed. These particular cloud formations measured between 20 and 55 miles across, and researchers determined they were associated with a meteorological phenomenon called microbursts. A microburst occurs when a concentrated column of cold, dense air inside a storm system suddenly collapses and plunges toward the surface. When it strikes the ocean, it doesn't simply create wind. It explodes outward in straight lines, generating localized wind speeds that have been measured at up to 170 miles per hour at sea level. For context, that wind speed is comparable to a strong Category 5 hurricane, but concentrated in a small, sudden, and largely unpredictable burst rather than a tracked storm system. The waves generated when these high-speed wind bursts strike the ocean's surface can interact and combine, producing localized waves up to 45 feet high in conditions that may have looked calm just minutes earlier. An aircraft caught inside one of these microburst zones could be struck by sudden, extreme turbulence and violent shifts in wind direction, strong enough to cause loss of control. A small vessel caught in the resulting wave field could be swamped or capsized within minutes, in what would otherwise have been unremarkable weather. Crucially, and unlike the methane theory, researchers studying these hexagonal cloud formations also identified similar straight-edged cloud patterns over the North Sea, off the coast of the United Kingdom. The phenomenon is not unique to the Bermuda Triangle. It is a broader atmospheric mechanism that happens to occur there. The third area of serious scientific interest involves something the ocean produces everywhere on Earth, but with a particular relevance to this region: rogue waves. A rogue wave is technically defined as any wave more than twice the size of the surrounding sea conditions. For decades, sailors who reported encountering them were often dismissed. Rogue waves were considered maritime folklore until 1995, when a wave height of 84 feet was directly measured by a sensor on an oil platform in the North Sea, finally proving scientifically that they were real. Oceanographer Simon Boxall, who has studied wave dynamics extensively, explains that rogue waves form when storm systems traveling from different directions converge in the same area of ocean. Individual waves generated by separate weather systems can stack on top of each other, briefly combining into a single wave far larger than any one storm could produce alone. The Bermuda Triangle's geography makes it a statistically interesting candidate for this phenomenon. Storm systems can approach the region from the Gulf of Mexico, from the equatorial Atlantic, and from weather systems moving east across the open ocean. Multiple potential wave sources converging in a relatively confined area. Boxall has pointed to one of the clearest documented examples of a rogue wave disaster: the sinking of the Ocean Ranger, at the time the world's largest semi-submersible oil drilling platform. which capsized off the coast of Newfoundland in February 1982 after being struck by a wave that overwhelmed its design specifications. That incident occurred in Canadian waters, not the Bermuda Triangle, but it demonstrated conclusively that rogue waves can sink vessels believed to be virtually unsinkable. A large enough rogue wave striking a smaller vessel in the triangle, in conditions that appeared calm only minutes before, could capsize or swamp it almost instantly. Consistent with reports of ships vanishing with no warning and no distress call. There is a fourth factor that researchers increasingly treat not as a single dramatic cause, but as a background condition that makes every other explanation more dangerous. The underwater topography of the Bermuda Triangle includes some of the deepest oceanic trenches on Earth. The Puerto Rico Trench, at the region's southern edge, plunges to depths exceeding 8,000 meters. This matters enormously for investigation. When a vessel sinks in shallow coastal water, wreckage is often recoverable, and the cause of sinking can be forensically determined. When a vessel sinks into trench depths exceeding 8 kilometers, in a region also swept by the powerful currents of the Gulf Stream, recovery becomes extraordinarily difficult, sometimes impossible with available technology. The Gulf Stream itself moves at speeds that can exceed 5 miles per hour through parts of the triangle, redistributing debris and wreckage across enormous distances within hours of an incident. By the time a search and rescue operation begins, physical evidence may already be scattered across hundreds of square miles of open ocean, or sitting at a depth no submersible was prepared to reach. This single combination, extreme depth and powerful currents, does not cause disappearances. But it explains why disappearances in this particular region so often remain unsolved, even when the underlying cause was likely an ordinary explainable event. Taken together, what does the current scientific picture actually look like? It is not one unified theory. It is several overlapping, independently verified natural phenomena. Methane hydrate eruptions, hexagonal microburst clouds, rogue wave convergence, and a uniquely difficult search and recovery environment, all occurring within the same geographically active stretch of ocean. Oceanographer Simon Boxall has offered what may be the most scientifically honest summary available. Each of these phenomena occurs in many places around the world. Rogue waves are not unique to this region. Methane bubbles are not unique to this region. What may be unique is the convergence, a higher than average concentration of these natural hazards occurring within one heavily trafficked, hard-to-search stretch of water, combined with a name and a reputation that ensures every incident receives outsized attention. The U.S. Coast Guard and the U.S. Navy, both of which have investigated incidents in the region for decades, do not officially recognize the Bermuda Triangle as uniquely hazardous. Most documented disappearances, when thoroughly investigated, are ultimately attributed to a combination of severe weather, navigational error, and mechanical failure. The same cause is responsible for maritime and aviation incidents anywhere else on Earth. What has changed is not the ocean. What has changed is our ability to study it. Satellites can now detect hexagonal microburst clouds from space. Sensors can measure rogue waves that sailors once described and were not believed. Submersibles can map seafloor craters consistent with ancient methane eruptions. The mystery has not been replaced by a single definitive answer. It has been replaced by something arguably more interesting: a set of real, physically grounded mechanisms, each individually documented, each individually capable of causing exactly the kind of sudden, unexplained loss the triangle is known for. The ocean did not need ancient civilizations or interdimensional portals to be dangerous. It only needed physics. This is Terrum.